The main objects of study in this course are linear functions. Now let's try to first understand what are linear functions. But to answer this question, perhaps we have to first understand what is the domain and codomain of interest. Let's take the simplest case where the domain and codomain are both the set of real numbers. Then we have the question, when do we call a function f from R to R linear? Maybe it's a good idea to pause your video and reflect what is this concept of linear function and have you encountered it before? I assume that most of you would have encountered linear functions, and you might say that a function f from R to R is linear if it has the form f of x is equal to ax plus b, where a and b are some constant real numbers. And this would be a correct answer. But we need to ask one question. Why are such functions called linear? What is the meaning of the word linear? Linear is a combination of two words, line plus r. Now r is something that you add to make a noun into an adjective. You might have seen many examples of this. For example, pole, polar. Polar means it's something to do with pole. So polar bear. Polar bear is a bear that is found in the poles. Or molecular. Molecule, molecular. Something to do with molecule. Molecular mass. So similarly, linear is something to do with line. So what you have to ask is, what does this function have to do with lines? And that's something you have to think. Now, the answer to this question is that the graph of the function f is a line. Now, many of you would be, or most of you would be familiar that this f of x equal to ax plus b is the equation of a line, and in fact b is the y-intercept, that means the place where the line intersects y-axis, and the slope of the line is equal to a. If you do not know this, please try plotting the graph of such an equation for a fixed a and b and convince yourself that f of x equal to ax plus b is the equation of a straight line. And this is why such functions are called linear. Therefore, notice that if b is equal to 0, then this line passes through origin. And this is in some sense important, so that's why I am stating it. We will soon see that somehow lines passing through origin are of more importance. And that is equivalent to b being 0. There is another speciality of this function f of x equal to ax plus b. Namely, f is a polynomial. And it is not just any polynomial, it is a polynomial of degree 1. This is pretty much everything that we want to know about linear functions from R to R. Now we change the domain and codomain. We ask, what are linear functions from R2 to R2? Now we should not expect that the graph of a function f from R2 to R2 is a straight line. Let us convince ourselves with some example. So for example, if you take the function f of xy to be equal to 0, 0, then in this case it's clear that you get the xy plane in the xyzw space. That means you are taking the first two coordinates to be non-zero and the remaining two coordinates to be 0 in R4. So what you get is a plane. Similarly, even if you take the function identity, that is f of xy is equal to x comma y, it is easy to see that what you are getting is a plane, not a straight line. So in general, it is kind of unreasonable to assume that you will get a graph that is a straight line. So what else can we do? How else can we define linear functions from R2 to R2? One way is to extend what we observed for functions f from R to R. Namely, that linear functions are given by polynomials of degree 1. So we can consider polynomials in two variables x and y of degree 1 and attribute that to each of the coordinates. So for example, we can take f of xy to be ax plus by plus c, comma dx plus ey plus f. Let's try to understand this better with some examples, okay? Because otherwise this is too abstract, right? In one dimension it was all fine, but in two dimensions it's too abstract. So let's try to understand this with the help of an example. Let us take a simple example. F of x comma y is equal to y comma x. Here we have taken b and d to be 1 and everything else, that is a, c, e and f, to be 0. So this is a linear function by the definition that we just wrote. Now let's try to see if this has anything to do with lines. So to do this, we will look at some lines, okay, and see what happens to those lines. So for example, one of the simplest example of a line is the set of all points x comma 0, where x belongs to R. What is the image of this set under F? The image of this set under F is the set of all 0 comma x, where x belongs to R. So what has happened here? This, if you notice, is the x-axis, and this, if you notice, is the y-axis. So the x-axis is being sent to y-axis. Similarly, it is easy to see that the y-axis will get sent to the x-axis. Now, what is a little bit more tricky is to see that every line gets sent to another line. So how do we see this? First, observe that an arbitrary line has the equation ax plus by is equal to c. Therefore, the set of all points x comma y such that ax plus by is equal to c is an arbitrary line. So what we have to do is we want to look at what happens when you act f on this set. Okay, when you act f on this set, you will basically get all y comma x such that ax plus by is equal to c. Now this is once again a line. And thus we see that a line is getting sent to another line. And this is a sense in which we can say that this function is linear. Let us now try to understand this geometrically or visually. The first time you try to do this, it might be a little difficult, but we need to get used to it. And I will try to help you along the way. So let's see what happens to a point, say 1 comma 0. A 1 comma 0, that point gets mapped to 0 comma 1. Now if you apply f on 0 comma 1, what happens? It again goes back to 1 comma 0. Now let us take the point, say 1 comma 1 by 4. Where does this point go to? This point goes to the point 1 by 4 comma 1. Okay. On the other hand, notice that every point that lies on the line y equal to x stays there itself. So if you take a point here, say 1 comma 1, then notice that the image of 1 comma 1 is 1 comma 1 itself. Or 0 comma 0 goes to 0 comma 0 itself. Half comma half goes to half comma half, and so on. So every point on the red line stays there itself. On the other hand, if you take any other point x comma y, it first gets mapped to y comma x, and then it again gets mapped to x comma y. So what do we see from here? F composed with f is the identity map. The next thing to notice is that if you draw the line segment joining 1 comma 0 and 0 comma 1, it is perpendicular to the line y is equal to x. Moreover, the point where it intersects the line y equal to x is a midpoint for this line segment. Now notice that the exact same thing happens if you are taken another pair of points x comma y and f of x comma y, which is y comma x. So in general, now I guess you understand what is happening. We are in some sense getting a reflection about the line y is equal to x. Now I want you to spend some time and convince yourself that that is indeed what is happening. So if you would like, pause the video and think about this for some time. To ensure that you have understood the discussion so far, look at another example. F of xy is equal to x plus y comma y minus x. Now I want you to repeat the exercise that we did for the earlier function for this function. Namely, show that this function takes lines to lines and understand this function visually or geometrically. Now, even though when we first looked at the function f of xy is equal to ax plus by plus c, comma dx plus ey plus f, we called it linear only because it was given by polynomials that are of degree 1. There was nothing that we saw which is related to a line. But now we see something that is related to a line. Namely, the two functions that we explored, they take lines to lines. So a natural question to ask is, does every function of the form f of xy is equal to ax plus by plus c, comma dx plus ef plus g take lines to lines? Spend some time thinking about this question, and we will see more about it in the next video.